Welcome to the class. Today we are going to discuss about sulfonation of benzene. Sulfonation is an example of electrophilic aromatic substitution reaction. Let's have a very short rewind of what is electrophilic aromatic substitution reaction. For this we have to look at the structure of benzene. So here is the benzene. Benzene has 3 double bonds. It has a total of 6 pi electrons which are in constant dynamic motion. So that constant dynamic motion results in two structures, canonical form 1 and canonical form 2. So the actual benzene is a combination of these two structures. These two structures where delocalization of electrons are taking place, or these two structures where resonance is occurring. So such a combination of these two structures is referred to as the resonance hybrid structure of benzene. Now, if I put electrophile into this system, the electrophile is positive. It needs a pair of electron. It needs an electron. For that, it attacks the benzene ring, but is unable to do so because the electrons are in constant dynamic motion. So this makes the benzene ring very unreactive. That makes the benzene ring very stable. Such stabilization, owing to delocalization of electron or owing to resonance, is referred to as the resonance stabilization. Coming back to our electrophile, if it is not able to attack the electron inside the ring, what option does it have? Yes, it can substitute any of the hydrogens in the benzene ring. The benzene ring has 6 hydrogen. It can substitute any of the hydrogen and take its position. And instead that H which has gone can combine with the base. Now that is what we call as electrophilic aromatic substitution reaction. Sulfonation is one of its examples. To understand what is sulfonation, first we will see the reaction and then we will go to the mechanism. Reaction. Let us see the reaction of sulfonation. For that, we take the molecule of benzene and react it with 2 molecules of H2SO4. So what we get is benzene sulfonic acid plus HSO4 minus plus H2O. So this is the reaction of sulfonation. Now let us see the mechanism. So as it is electrophilic aromatic substitution reaction, there are 3 steps. It occurs in 3 steps. Let us see step number 1. Who is the problem maker here? Yes, the problem maker is SO3H. Let us see how SO3H comes up. That is step 1 is formation of electrophil. Electrophil is the problem maker. So that should come out. Let us see how it comes out. I am going to write the first molecule of H2SO4 like this, HSO4 minus, and the second molecule of H2SO4 like this, H2O SO3. Fine. Now the function of H2SO4 is to release a molecule of acid, that is H3O plus. So this would combine with this and they may become H3O plus, and we get SO3, okay, sulfur trioxide, and we get HSO4 minus. Now these two they combine to give that H2SO4 and H2O. Okay, we are not bothered about this. SO3 plus has formed. Okay, the positive sign lies on the sulfur. Okay, we will see how But the structure of SO3 we will see, and you will come to know how that positive sign comes on S. Okay. Let us see how positive sign comes on S. So we got the SO3 plus. Now let's see how positive sign comes here. This is SO3, fine. And what happens is, because all are electronegative, so one of the oxygen pulls, and what would happen? Yes, that would become negative and S would become positive. This negative sign, it may come here, and the second oxygen pulls the electron. So what would be the net result? Would be this. Okay. Now the third oxygen pulls the electron, and it would become something like this. Right? So overall you can see that SO3, the resonance hybrid, the delocalized structure of the SO3, the hybrid structure of SO3 would seem like this, with the positive sign lying here and negative sign lying here. This is delta positive. Okay. So the SO3 plus is the electrophile, which is very clear. Okay, so the step 1 is over. We have seen how SO3 plus is formed, and we have proved that how S is positive. Let's go to the step 2. The electrophile has now come into this picture, has come into the system. Do you think it would sit idle? Definitely not. It will go and attack the benzene ring, and it will form, and the benzene would be converted into a carbocation. So the step 2 is formation of carbocation. Formation of carbocation. Now your benzene ring is here. I'm going to draw the bond here so that I can show it here. Now SO3 plus, fine. Now let's see, the positive electrophile takes this electron pair, suppose. Then what would be the structure? It would be like this, SO3, and I am drawing H here. Actually all the carbons are having H, but I am drawing H and specifying or depicting H here for the purpose of better understanding of the mechanism. Now as you can see, a bond is made up of 2 electrons. The electrophile took this electron. Okay, the electron here that remained with this carbon, but this electron, the electrophile took it. So the loss is with this carbon. Fine. Now after this is not stable state. To compensate the loss, the electron pair will be shifted from adjacent carbon. When it gets shifted from this carbon, the loss is not with this but with this carbon. So the second structure that we get is like this. So we get positive sign here, and we get bonds here. Now to compensate for this positive sign, this electron pair, the bond will shift here. When it shifts here, there is no loss for this carbon but for this. So positive sign will come on this in the next structure. Let us see. So here the positive sign comes, and here we go, SO3 and H. So overall you can draw a structure like this, which would be an adding of all these structures. You will get something like this. The positive sign, as you can see, it's keep on rotating around different positions, which is perfectly depicted via this structure. Now benzene is actually electron rich species. This state is very unstable. A carbocation state is very unstable. So it tends to take its electron pair back and restore the negative sign. So that we will see, that we are going to see in step 3. So step 3, I hope it is clear. Step 3, is your abstraction of proton. Abstraction of proton. Let's see what happens. So we are going to draw our unstable carbocation here. Everything, the positive sign is rotating. This is SO3 and this is H. So I am going to draw SO3 in a much more detailed manner. I am going to draw the 3 O's. This is the first O, this is the second O, and this is the third O. Now one O is negative here. So now what would happen? The carbocation, the benzene is unstable in such a condition, so it takes its electron pair into the system. When it takes it into the system, the H plus is released and it goes and attaches to this. Now what we get is benzene sulfonic acid, SO3H, benzene sulfonic acid. Dear students, sulphonation of benzene is what we have studied. It is an example of electrophilic aromatic substitution reaction in benzene. There are other examples of electrophilic aromatic substitution: Wedelicid, bromination of benzene, nitration of benzene, Friedel-Crafts alkylation and Friedel-Crafts acylation. I hope you understood the class. Please subscribe to the video. Thank you very much.